Hello everyone and welcome to the third video of my crafting interpreters in Swift series. On this series, I walk through my implementation of the logs interpreter in Swift. If you haven't watched the two previous videos, I really recommend you to watch them, as in them I introduce the series and in the second video I talk about how the scanner works. In this video we're gonna take a look at the parser to see how it gets the output from the scanner and it works with that list of tokens to create our syntax tree. On the previous video we stopped at the scanner state. If you remember, we have this temporal file that we use to write our logs code to have some code to work with. And in the previous video we just output the result of the scanner. You can see here the list of tokens, but now we're gonna go and take a step further. So we're gonna comment this print and we are gonna uncomment the parser stage and do the same and print the output from the parser to take a first look at how things work. Okay, this is interesting because as you just saw, the tokens array was there, so the scanner worked perfect. It didn't have any problem. But now when we try to go to the next stage and start parsing, the parser immediately gives us an error at line 2 that we are missing basically a semicolon. If you go to the text file, you see that indeed here this is not valid logs. Basically we wrote that on the previous video to demonstrate something, but this is not valid logs. So what we need to do is get rid of that part, save the file again and run it, and now we can see what it's the output from the parser. This is the syntax tree that we're going to be working with. We can start comparing it with our text and go through the code. The fact that the scanner accepted that wrong logs code and the parser didn't, it's something that is really important to understand, and that sometimes, as I said before, it's hard to know where to catch some errors and where exactly put that code. But in this case it's quite easy. Like, the scanner just gets the bunch of raw string text and it breaks that down into a list of tokens. It doesn't matter if you can group the tokens correctly, it just matters that it understands what the tokens are. We already talked about that on the previous video, but in this case the parser is the one responsible of putting together those tokens. If there is a sequence of tokens that doesn't match anything the parser understands, then the parser needs to throw an error. The structure of the parser is similar to the structure of the scanner. Basically, if you think that the scanner iterates over an array of characters in the string and it outputs an array of tokens from those ones, grouping them together, the parser does a similar thing. It just iterates over the array of tokens and then it needs to group them together to create the statements that make our program. The implementation of the parser, it's basically a code recreation of the syntax grammar of the language. In my opinion, this is the difficult part of designing a language. You need to get the syntax grammar right, not only for the user of your language, of how to write it, to make it easy for them to write and to remember, but also, depends on what you do, it can get really tricky to create then the parser. In this case, we have the syntax grammar for logs that the book gives us, that Bob created, and we see that the grammar starts with a top-level declaration. And then it recursively gets down into more specific declaration types, and some of them even go next level deep. Let's start taking a look at the code of the parser. So the parser is just a class, as the scanner was, and then it has an array of tokens, which is the input that in this case we receive from the output of the scanner. And then it keeps track of the current token that it's parsing. This other property here is specifically to know at which loop nesting level we are. In case that we find a break, we need to know where to break. And then, as usual, the only public function that we have on this class is the parse. The parse function, it just iterates over the entire array of tokens, trying to group them together to create our array of statements. We can compare here the language grammar with our code, because the parser is a literal representation of that grammar. If we take a look here, the first thing we do is check if we find the declaration, and that matches what our grammar says. First, the most top level thing we need to check is for the declaration. Then, if we go inside the declaration, that declaration starts following what we have on the right side of that declaration grammar. We first check for a class, then we check for a function, then we check for a variable declaration, and if none of these special cases are found, then we fall back into a generic statement. This is called a recursive descent parsing because, I mean, that's what the name implies. It just recursively goes down through the tree of our grammar, trying to group those tokens in a meaningful way. If we just follow here the class declaration, for example, we see that it's in the next level, in this case here, and at this level, it's where this branch of the tree ends. In this level, we literally start taking a look at what a class declaration represents. And the important thing here is that when we are at this level, we don't take a look at the first token. In this case, we don't check that we found a class, because that check is already done on the previous level. See, in this case, we were already checking if there is a class, and that was the clue that we needed to go inside that branch. So for that reason, we don't need to check for that again. So after we know that we have a class and we get an identifier for the name, every time that we check for something in this consume or in this match, we are trying to make sure that the token that we are reading now matches with what our understanding of a meaningful group means. In this case, we're trying to parse a class declaration, so we try to get an identifier that will represent the name. At any point on these checks, it can fail. So what we do is just we throw a Swift error that will just return immediately at this level of our function stack, and we'll try another branch. Basically, you can see here as in this class example that the code pretty much matches what the grammar says. We take the name from an identifier, and then we check that we find the last token, and after that an identifier, and that will mean that we have a superclass. But if we don't find it, in this case, we don't throw an error, because it's okay in this language to not have a superclass. After that, we take a look at if we find a left brace, which will indicate the start of the body of our class. And then we will take a look at the right brace to finish that body. And for the body, it's again where we see the recursivity taking action here. We take a look, basically, if we haven't found the end of the class body, which is this thing we're checking here, and we are not at the end of the file, then we're trying to parse the function, because that's the next level on our grammar. At the end, when we have all the pieces, we have the name of the class, we have the superclass, or nil if there was no, and then we have all the methods on this class declaration, we're finally gonna create an instance of this class that it basically creates the statement. It's a good moment to take a look at this statement class. Basically, here we have our class, or all our classes that define every kind of statement that we have, and this will form our abstract syntax tree. And then all of them conform to this visitor protocol, which will help navigate the tree easily for different reasons. I mean, one of them will be obviously to interpret the code, but another one will be to make a semantic analysis pass. All this code is code that we haven't written manually ourselves, because you see all the statements of classes that we have the same form. They have the properties that they need, they have initializer, and then they have this accept function that just integrates the visitor pattern. This is automatically generated with another module that we have in the project, that is the generate.ist, and here is where we define the expressions and the statements, and then we just run the command line tool that we created for this, and it basically creates that file that we saw, and we don't have to modify it. If we continue to take a look at the parser, we see that every function just represents a level of this grammar tree, and we just keep going down recursively through it. The for statement is an interesting case to take a look. The for statement is common on every language. It's basically another kind of loop, the basic one usually being the while loop. I really like it implementing the for statement because it showed how syntax sugar can be easily added into the language without affecting the low-level machinery too much. In this case, a for statement is just another way of writing a while. What we do here is we start taking a look at how a for statement is defined. So freeze, we don't need to take a look for the for keyword because we already know that we are at this level, so we already found it. That's fine. Then what we try is to find for the left parentheses, and then we try to find the initializer, so the freeze part of what we put inside the for. Then the condition, and finally the increment part. This is the three parts that we put every time in a for. As we can see, some of them are optional, so we don't need to put them. And finally, just a special thing that we need to do here when we are creating these loops that accept breaking out of them. As I said before, we keep this variable around to know at which level we are. Then we parse the body, but the interesting part is here. This for loop doesn't have a statement class. What we do is we then create manually our tree that represents this for statement based on the while loop. So we start creating this body representation. So we start by adding the body that the developer wrote, and then after that we add the increment expression. So first we run the body, and then we run the increment expression. We grab all of this and we put it inside a while with the condition given, but then we're missing the initial step, the initialization of the variables. So what we do is we wrap again all this while with the initializer statement that we had, and with this we created a while structure based on the for loop that the developer wrote. So this is really interesting because we just added a bunch of syntax sugar to make things more natural for our users without compromising the structure of the interpreter or the semantic analysis. Like basically any step that happens after the parser doesn't know that our language supports for loops. The rest of functions that we see here, they just follow more or less the same pattern, so there is not much interesting to see, except maybe mentioned again that the print statement, we have a specific statement class for it because this language represents the print function as an integral part of the language, and this was basically for teaching purposes because Bob wanted to have a simple way to output what we were writing while we were recreating all this. Without this, we wouldn't have been able to see any output from our code until we added all the stuff about functions and all that stuff. So by adding the print statement as an integral part of the language, we had this straight away. And then the rest of them are just more the same. You can see that some of them, they go recursively down and down and down. There is no need to take a look at all of them. What is interesting to take a look is when at some point the parser finds an error, it calls this synchronize function. As we can see in the top level declaration parsing, if there is an error from anything, it just tries to synchronize. So error handling is the hardest part of writing compilers. You want the compiler to not crash or not hang indefinitely when it finds an error. What you want is you want to detect and report good errors, especially with great context around them, like the line numbers and any information that you can provide to your developers. And then if you want to go the extra mile, you can even suggest fixes that the IDE can perform automatically for the developer. And then if you are amazing, you can even predict what the user wanted and make more meaningful suggestions. There is something the Elm compiler is well, basically one of the best ones out there on trying to do this. If you make some typo, it even tells you, well, you probably wanted to write this, so use this word instead. And that's great for developers, especially when learning a new language. But this is super hard to do. And not only that, but what the developer expects is that if it's writing something that it's wrong, it wants to see the reports from multiple errors at once. It doesn't want to see one error, fix it, see another, fix it. Like that iteration cycle, it's not good at all. So we want to report multiple errors at once, but then we want to avoid reporting errors that are caused from the first error, because then you're just lying to the users, like, well, if you fix the first one, you will fix all of them, so there is no need to report all the others. The way it's implemented here, it's with this synchronize, is it keeps consuming all the tokens until it gets at the end, and until it finds a synchronization point which it basically means that it gets out of a nested context. And after that, it basically has ignored all the tokens that were at the same level as the error was found, and then it pops up to a different context, and it tries to continue parsing. I really like this way because it teaches a way to do error handling in an interpreter without super complicating the structure itself. Finally, what I need just to show you is this parsing infrastructure here. This is basically all the much, the check, the advance, the peek, previews, and the consume are all these functions that the parser needs to iterate through the list of tokens. This is similar to what we already did for the scanner, but in that case it was to basically iterate over a string, over every character and check the next character and stuff like that. So that's pretty much is the same thing, but for an array of tokens. And I think that's everything for the parser. Now we could take a look and see how the original file that we were running, it gets interpreted. So as we can see, we have a class food that has a function initializer. That function initializer has an assignment for the property that is this name, and it's assigning apple. So as you can see, this output is representing the abstract syntax tree, not in the nicer way, because it will be super nice to see the tree and all the branches and everything, but you can read it easily. And with this, we finish this video about taking a look at the parser. We already went from original string that the programmer wrote. We created an array of tokens in the scanner, and that array of tokens has been used to create the abstract syntax tree in the parser. The next step is talking about semantic analysis, but that's going to be in the next video. Thank you for watching, and remember to like if you liked this video, and to press subscribe and the bell if you want to be notified when the new video comes up.